Welcome to our talk on stateful streaming, how to update decision logic at runtime. Before we begin, I'd like to give a short introduction. Mathieu and my name is Alex. We both work as software engineers at Payback. Payback is a German company based in Munich and is part of the American Express Group. And Payback is a loyalty program, which basically means that whenever you as a member purchase at one of our partner stores, you can collect points, and these points you can then use later on to save money on future purchases. And Mathieu and we both work in the real-time marketing team. The team has built a streaming system around Spark streaming, where we receive millions of events every day. We receive these events via Kafka and then react in real time, for example, by sending out an email, sending out a push message, or assigning a coupon. And this process of receiving an event and reacting on it is what we call a marketing campaign. And that leads us to the topic of our talk today. The situation which we are in is that we run many of these marketing campaigns simultaneously, and also they contain very business-specific logic. The challenge which we face is we don't want to be responsible for hard coding these campaigns, and also we don't want to redeploy our Spark job each time there's a new campaign. And we came up with the following solution, that instead of hard coding these campaigns, we read them from some external source. In our case, this external source is Kafka, and then we treat the campaign as internal state. And exactly how we do this will be the topic of our talk today. So first of all, Mathieu will go through the basic concepts behind stateful streaming. Then I will show you our implementation with some code examples. Then we have a demo prepared. And finally, we have the most important takeaways. And now over to Mathieu.
So first, the typical stateless streaming that we all know and love and use, at least for us on a regular basis. You have a typical Spark streaming job. You have an event coming in, and we process that event. And based on that event, we have some form of output. And each of these events then is processed completely independently. And that means that if ever the job needs to be restarted, or if the job fails, then we can just continue processing from where we left off. A simple example of how this can work. So for example, you have an event that's coming in. Let's say in our case, we have a Payback partner that's a grocery store, and one of our members purchases something at this grocery store. Well, then we can process this information and send out, in this case, for example, a push message saying, "Thank you very much for your purchase." So each message coming in says this member purchased something, and for each member, we send out a push message. Obviously, in reality, we would probably do more than just "thank you for your purchase," probably include some coupons or various other things like that. But just as a simple example, this is generally how it works. So then we can move on to stateful streaming. So in this case, we process the events, and the way we process the events can be dependent on previous events. So we need to keep track of information from the previous events, and when we process new events, then we process them based on this extra information as well. This adds a bit of more complexity if we need to recover the state once a Spark job restarts or something like that. And it's not possible to simply reprocess events that have been previously processed, because then you'll add the state, you'll make a change to the state again, and that will make the state inconsistent. So we can have a simple example of this too. So we have a purchase transaction coming in again from one of our members from a grocery store, let's say, and we have a specific campaign running where you get a certain thing, say a coupon, when you've reached a certain amount of purchases in euros per week at this grocery store. So for example, then you have a purchase transaction coming in. We look at how much you've purchased that week, and then we send you a push message saying, "You've shopped for X amount of euros this week." So imagine that somebody shops for 100 euros on Monday. We keep track of that in this case, our database. And then we send out the first push message saying you've shopped for 100 euros. And let's say Thursday, you do another purchase for 35 euros, then we will keep track of that. And then we send out the push message saying you've shopped for 135 euros this week, for example, and so on and so forth. So the streaming the stateful streaming that we want to talk about in this presentation is slightly different. Our state, it comes from an external source, completely separate from the events. And so this is not necessarily dependent on previous events. This means that every time we start our Spark streaming job, we need to make sure that we read the state coming in from an external source and that the state is all consistent and ready before we start processing events. And that has the big advantage for us that we then can change the state during runtime. So we can have a certain state when we start up and then sort of on the fly change it as we go along. So a simple example again is we have a purchase transaction coming in and we have a certain campaign going on that where we give a certain amount of discount in euros to the user. So in this case, we set a state and the state is that we have €5 discount being given out to our members. So we have a purchase transaction coming in. We process it. We see that the current rule is a €5 discount. And then we send a push message to that member saying, here, you've got a €5 discount. We can then change that rule on the fly without redeploying our Spark streaming job. And then we can say, okay, no, actually, we want to give a €10 discount. So here we give a €10 discount. We update the rules, and then every single event coming in afterwards, every single purchase from that grocery store, for example, will result in us sending a push message saying that you've got €10 discount. So obviously, this is a very simple example. In our case, these rules can get quite complicated. We'll have different target groups where we target certain users based on their history, and certain target groups or groups of users will get this coupon, other groups of users will get this other coupon, for example. We can have campaigns where the members need to reach certain goals, and we can have big complex logics on how they can reach those goals, like we talked about in the previous slide with a certain amount of euro purchases per week at a grocery store. We have all kinds of very complicated rules. And so this is very advantageous to us because then we can update these rules sort of on the fly, as you can see here in this simple example. Another way of maybe paraphrasing it or seeing it is, I mean, many of you come from a machine learning background. You often have, for example, for fraud detection, you have different fraud models, and you want to be able to update your fraud models on the fly without having to deploy your system completely anew or restart your streaming job or things like that. So this is sort of very similar how we use it. So how does this work with concurrency? So obviously our Spark streaming jobs run concurrently. So we have different executors that process different events with different outputs. And each of these executors also read the state. So we don't have these executors change their state by themselves related to or based on what they read, but instead we have this state sent to the driver, which is sort of a central processor or a central organizer, excuse me, of these executors. And this driver collects these state changes. And then the driver updates the information about the state. And then the driver can then decide when it's a good time to broadcast the complete changes back to the executors. And this can be done at a certain frequency. And this ensures then that each of these executors gets the new state at exactly the same time so that we are consistent, basically. Instead of each of these executors reading the state and updating their own state themselves, we use this approach. And Now we'll go on to talk more about how we implemented this and a bit more detail on the actual code behind all of this.
Okay, now let's take a look at our implementation and also go over some code examples. Throughout this whole section, you'll see a small diagram in the corner. That's the architecture which Mathieu just explained. And on each slide, we will highlight a different part of the architecture, and so that we can see where in the code we are at exactly. Okay, good. Let's start. First of all, we would like to come up with some way how we can broadcast data from the driver to the executors. And also each time when we receive an update on the driver, rebroadcast this update to the executors again. And Spark already offers something pretty similar. It's called a broadcast, but this is only immutable. So we can only broadcast data once and not update it again. So what we did is we came up with our own class called Mutable Broadcast, which is basically a wrapper around the Spark broadcast and holds it as a var so that it can be changed later on. And this Mutable Broadcast class has two public methods. The first is give me the current value, and the second is update with something new. Give me the current value is pretty straightforward. And for update with something new, what we do is we get the broadcast and delete it, or in other words, call the destroy method on it. But as the broadcast may currently be used somewhere else in our application, we don't want to do it immediately, but we wait for one microbatch, so in our case 2 seconds, before we call the destroy method. And at the same time, we create a new broadcast with the new data and reassign our broadcast holder var to this new broadcast. So that way we have something which we can broadcast data from the driver to the executors. And whenever we receive an update on the driver, rebroadcast this update to the executors again. And what we need this for, you will see on the next slides. So let's take a look at the diagram again. When we start up our job and before we begin with the actual streaming part, we'd like to do a batch read where we read everything which is in the Kafka state topic, collect it to the driver, and rebroadcast or broadcast it to the executors. Okay, let's begin with the code. So the first thing we do is we do this batch read from Kafka. And for simplicity, I won't show the code in there, but I'll just shortly explain it. So the first thing in this batch read from Kafka method is we create a new Kafka consumer, then read the beginning and ending offsets for each partition for the state topic, then close the consumer again, and then use the Spark native method for reading from Kafka for these given beginning and ending offsets. And that way we have an RDD of all consumer records, which we read from this Kafka state topic. Then next step is that we map this RDD of consumer records to an RDD of our own class, which we called record. Then we collect it to the driver and remove duplicates. And again, for simplicity, I won't show the code of this remove duplicates method, but it's pretty simple. It's just grouping by key and only keeping the newest timestamp. And then the last thing we do is we instantiate a mutable broadcast with this initial state. So mutable broadcast is this class which you just saw on the previous slide. And by instantiating this, we broadcast the initial state to all executors. So let me give you an example. Let's assume there were 3 records in the Kafka state topic, record A, B, and C. And when we started our job, let's say executor 1 read records A and B, and executor 2 read record C. Then we collected it on the driver. So there we then had the sequence of records A, B, and C. And by creating the mutable broadcast, we then broadcasted this sequence of records A, B, and C to executor 1 and also to executor 2. Okay, let's continue. Now, if we look at the diagram again, we would like to process new events which we read from the state topic. So in other words, if there's an update to our state, we would like to read this, collect it to the driver, update our broadcast, and rebroadcast to all executors. Now let's take a look at the code. We're reading from the event topic and the state topic. And as we're only interested in records from the state topic, we filter our streamed RDD only on records from this state topic, and then we call our update method. In the update method, again, we map our RDD of consumer records to an RDD of our own class, which is called record, then collect it to the driver. And there we add all new records on top of a sequence of the previously read records. And if necessary, we have to remove duplicates here. And then we update our mutable broadcast with this new state. And by doing so, we rebroadcast this new state to all executors. So if we continue with our example where we read records A, B, and C previously, and somebody posts a new record, let's say D, to Kafka, let's say executor 2 reads this new record, we then collect it to the driver and add it to our existing sequence. So now on the driver, we have records A, B, C, and D. Then we update our broadcast, our mutable broadcast. And by doing so, we broadcast records A, B, C, and D, both to executor 1 and executor 2. And now to the final piece of our puzzle, the actual processing of the millions of events, which we process together with our internal state. So let's look at the code. Again, we're reading from two topics, the event topic and the state topic. And this time we're only interested in records which we get from the event topic. So we filter our streamed RDD and call our process event method, which looks like this. And let's assume that the events which we receive are purchase transactions. And to keep it simple, they only contain the name of the person who did the purchase. And for each purchase transaction which we get, we would like to send out a message with the name and together with two placeholders, a greeting and a discount amount. And instead of hard coding the greeting and the discount amount, we'd like to get it from our internal state. So let's assume in our example with the records A, B, C, D, which we read before and are now storing in our internal state, that they are not just A, B, C, D, but rather key value pairs. So let's say one of them says greeting equals hello, and another record says amount equals 5. Then each time we receive a new purchase transaction, we can then send out a message with the greeting and the amount which we queried from our internal state. So let's say we get a purchase from Lisa, we then send out a message saying, hello Lisa, you got a €5 discount. And I know this has been a lot to take in, and in case you got a bit lost along the way, don't worry. We've got a demo prepared and this should make things clear.
I'm going to give you a short demo of the things that we talked about in our previous slides. So here, in the middle here, we have a representation of the Spark streaming job. So we actually have an actual job running currently that is using the exact same code as we have in the code examples earlier. So this Spark streaming job that's currently running is going to get some input from a certain Kafka topic. So this Kafka topic is going to be used to specify the events, in this case, the purchase transaction. So if a certain person makes a purchase at a certain shop, we will get an event here. And then as the output of our Spark streaming job, we will have another Kafka topic that's used to send out push messages. So we will see which push messages are sent to the users. And last but not least, our Spark streaming job here will have a state, just the way we described it earlier with the same code. It's going to be specified in a Kafka topic as well. And well, let's start with our state here maybe. So the output is going to be a push message, and the message needs, well, obviously a greeting. So let's start with a pretty formal greeting. And we are also going to give a discount amount to the user that purchases something. So let's start with a smaller amount, let's say €5. So here, so we have our state now, it's defined here, and then we'll have a person make a purchase. So in order to simplify this demonstration, instead of a full purchase transaction information that we have with amount and everything else, we'll just put the name of the person performing the purchase just to simplify things. So here I'm going to add myself there, and I'm going to make a purchase and check my phone to see if I get a push message. And here we see, oh, look, dear Matthew, you got a €5 discount. How nice. Huh, I should go shop there again. So now we, as a team, talk to our product team, and they say, wow, this campaign is running really great, but you know what? I think we're losing the attention of the younger people in the crowd, you know, that are getting this push message. They're not paying attention to it as much. So how about we try to do something that catches their attention? And they say, okay, could you change the greeting to something a bit more, you know, hip and cool? So let's do that. So now we have a new greeting, a hip one and a cool one. And I'm gonna go shop again. And all of a sudden I check my phone and I get, oh, howdy Matthew, you got a €5 discount. And I say, wow, that's a pretty funky message, I like it. And all the other hip cool people out there think so too, and so the campaign runs even better than before. And then we get a message from our product saying, the campaign is going great right now, has a good momentum. What we need is more coverage on social media. So we really need some wow factor here right now, quickly. And so we decide, okay, for a short amount of time, let's change the amount of discount to a very large amount just to get people's attention. So that's what we do. And this time, the lucky shopper is going to be Alex. And as we can see, Alex on his phone is going to get, howdy Alex, you got a €100 discount. So as you can see, we had the same Spark job, the Spark streaming job running in the background. We didn't have to restart it at all. We were just able to change the state on the fly here and change how the campaign worked. Obviously, in a real campaign, we have much more complex logic than all of these short messages and things like that. But it does illustrate the fact that we can change it on the fly very quickly and adapt to any situation that arises. And so that's a short demonstration of this stateful Spark streaming job, and we'll continue along our presentation now.
So as you saw in the demo, by avoiding hard coding these business rules, we can save a lot of time and effort. Then we can create and update campaigns pretty quickly, and also keep in mind that the example in the demo was pretty simple. It was just two placeholders, a greeting and a discount amount. But in our actual system, the campaigns are much more complex. They can consist of JSON files with all kinds of decision logics, and as Mathieu explained earlier on, target groups and all kinds of stuff. Then, as we are now reading our decision logic from an external source, we need to be more cautious, and especially our system needs to be made fail-safe. And end-to-end testing becomes quite a bit more complex. And in our examples, we used Kafka as an input, but our implementation isn't confined to Kafka. You may use any other input source, for example, a database if you like. And also one last thing I would like to say before we finish. So if any of you are considering to do something similar, please just reach out to us. We'd be really happy to help. We've been working on this for a few months now, and there have been a couple of pitfalls which we've overcome. For example, we wanted to use a compacted Kafka topic for us to read the state from, but we run into some performance issues there. And yeah, we'd be really happy to share anything which we couldn't cover in this half-hour talk.